I'm a meteorologist. You guys know what that means?
You are our introduction to weather. They have very little background right now, but we're going to use you as our jumping off point.
All right, I gotcha. So
and I'm going to go play with the blinds because there's a glare.
I gotcha. So basically, you know, there are meteorologists that present the weather. You see weathermen on TV that have the green screens behind them that talk about what weather's coming. There's people who do that research. There are a lot of people that help with creating some of the models that you see, which are on TV. You know, when you see a hurricane coming, there's a 5-day model that comes out. There are a lot of research that goes into that. But what I like to do a lot is I forecast for radio stations, for TV stations. The Mets were in the World Series. We were doing the forecasting for them as well. They did win. But we do stuff for baseball clients. There are people like if you're in the city and you see sanitation people or the people dealing with the port, with the oil rigs, we deal with those as well. But the biggest thing that I do is forecasting. And I know that's what you guys really want to get used to doing. If you look at a weather map, just to see, okay, if there's rain coming over here, how long will it take to hit me? If there's a storm coming in, will it hit us or will it miss us? If there's a hurricane, is it going to hit us? If there's tornadoes, are we in a dangerous area? And knowing about what goes into the technology that creates that really helps with forecasting and helps you guys, even without any training whatsoever, just look at a weather map and see, okay, this is coming to me. Now, I'm sure that many of you guys have seen forecasting services before, so let me load up my video here. Share screen. If I look at your forecast right here, this is Grapevine, Texas. So right now it is, let me just refresh this. So right now it's 60 degrees outside. There's a little bit of fog and mist. Today it's going to be 76 degrees and sunny. Tomorrow it's about the same. Wednesday it's about the same. So how do we actually know that rather than just looking at your forecast or turning on the TV and they tell you what's going on? Why is it sunny and clear? Why is it sunny and clear? Why on Wednesday night all of a sudden is there thunderstorms? Well, first you could look at a weather map. And you guys have seen this plenty of times before. There is only rain right now over the southeast. There is rain right now over the west side, going over California, which really needs rain because they're in a drought. But there's nothing over here. And if we look at any clouds, there's some clouds over here. The Dallas is over here. There's a little bit of wisps with the clouds. But other than that, all the clouds are where the rain is. There's rain over here where there was a hurricane. There's rain and winds over here. If you put both of them on the same map, you can see that most of the time if you see rain, there's going to be clouds in it. If you don't see rain, there may not be any clouds whatsoever. And if I look over here, you can see every one of here is sunny. So if I zoom in, all that is sunshine. But here's some clouds, and you can see where all the gaps are. So you can see here, this is a really, really large area of sunshine, which is why your weather for today is going to be sunny. But how do we know that tomorrow is going to be sunny? How do we know that Wednesday and Thursday are going to be, well, Wednesday is going to be sunny, but Wednesday night there's going to be any rain? The biggest thing that we do is look at models. So if I look at a model of, let's say, 4 days out from here, so Monday through Thursday, I just click on this and it loads up the models. This is right now. If we go a couple of ticks into the future, this is now midnight. So you can see here there's rain. There's still nothing over here. And if you go back to that forecast, you can see here it's clear skies. There's nothing going on. Go a little bit farther into the future. We're now Tuesday during the daytime. There's still nothing here. There's high pressure, which means that there are no clouds. High pressure usually means that there's no clouds. It's a little bit cool. It could be a little bit cooler, but it's very sunny out. There's not going to be any rain. Low pressure, which is what this is over here, low pressure or here as well. Low pressure means that there's going to be a lot of rain or there's going to be a lot of clouds or any severe weather if there's very strong low pressure. But you can see over here, this is now Tuesday. Tuesday over here, it says that it's going to be sunny. Tuesday, there's nothing over here. Going to Wednesday, there's still nothing. But Wednesday night, you can see here now there's a lot of green. And that goes with Wednesday night, there's a chance of thunderstorms. Going into Thursday during the day, this is very deep green, which means that there could be thunderstorms because it's warm out. So models are a very good way for us to see physically where the weather is and where it's going to hit us. That's why you could, if anybody looks up the weather on these models, which I could give you the links to as well, you could do this on your own, you could see just why there's going to be thunderstorms on Thursday, but today, tomorrow, and Wednesday are going to be completely sunny. As far as anything else goes, let me just load up what I have here. as far as anything else goes, you guys wanted to know about severe weather systems as well. So, and how maybe the ocean deals with that, and the land itself. So, what type of severe weather do you guys know about? You could just shout it out. Just name some severe weather. Tornadoes, hurricanes, right? What else?
Tsunamis, earthquakes.
Exactly. Yeah, tsunamis and earthquakes. What causes tsunami? The earthquake, right? Do you guys know about tectonic plates yet?
Yes.
Okay, so you know that when there's an earthquake in the bottom of the water, and it either comes together. There's a couple of different types of earthquakes that could happen. There's submersive, which they combine together, and the earth literally comes upwards and creates shock waves. That could create tsunami because all of a sudden all that water that was over here is pushed up and goes right to the ocean, the surface, and creates those tsunamis. There's also earthquakes where the plates go over each other, right? That's a little bit less destructive on the earth, but it still causes a lot of shaking. It just doesn't cause as much tsunamis. And the third one is if one is on top of each other and it just flips up like that. That causes a lot of tsunamis as well, because that's meaning the water goes directly up into the sky. Into the sky if it's on land, or up towards the surface of the ocean if there's water. As far as how the water actually has to do with the land, you guys mentioned hurricanes. On the large scale, if there's a lot of water that's warm, hurricanes will most likely form if conditions are right. And all the hurricane with the water and the winds, they'll start to move onto land. So that directly affects the land. On the smaller scale, if I go to, well, let's see, you guys are right over here. This is Grapevine Middle School. If I zoom out, you can see Texas starting to form. So you guys are right over here with Texas. Go a little bit farther out, this is the United States. Over here, these are the Great Lakes. So even though it's not an ocean, these lakes, whenever there's moisture, and whenever there's any energy, that could create weather systems. So have you heard the term lake effect snow or lake effect rain? That means that there's winds moving over these Great Lakes and picking up the moisture and then dropping it right over here. So a place like over here is Buffalo. Last winter, they got 7 or 8 feet of snow in 24 hours. That's only because of the fact that there is so much wind and so much energy coming off of the lakes, and it dropped it directly on top of Buffalo, which is directly in the path. That's lake effect snow. So that's one small way that lakes can affect, that lakes or any masses of water can really affect the land itself. You also have, a little bit closer to you guys, there are tornadoes that form over here. The reason for that is, and I have a little map that shows that. So you guys know what Tornado Alley is? It's an area that is part of Texas. It goes up to Oklahoma. These are the Great Plains states. So the only reason why there's a lot of tornadoes here, actually in the entire earth, this area of the United States has the most tornadoes by far, in I would say thousands more hurricanes than any other area in the world. I think actually if you tally up all the tornadoes in the world, and then tally up all the tornadoes that are just by you guys in Texas and going up all the way into the Great Plains, there are more tornadoes in this area than there are in the entire world combined. The reason for that is global patterns, which you guys want to learn about as well. There's something called the jet stream. You guys know? Have you guys know about the jet stream, or have looked that up before?
Not yet.
You know what it is? Okay. Jet stream is basically winds that are very, very high in the air. It's 5.5 miles up. You guys, have any of you guys been on airplanes?
Yes.
So you guys heard what, sometimes they say, okay, we're now at our cruising altitude. You've heard that term before. Cruising altitude is 30,000 feet or 5.5 miles up in the air, anywhere between 30,000 and 35,000. The reason why that's called cruising altitude is because the jet stream is right there, and that pushes the plane even more. So think of if you're standing still, right? If you're running into the wind, it's harder to run. But if you're running and the wind's behind you, you go faster, right? It takes a lot less energy for you to run. That's because the wind's pushing you forward. The jet stream is that. If you're at 30,000 feet in the airplane and you hear cruising altitude, the jet stream is pushing you faster. And that's a big driving force of a lot of weather. So I'll show you that a little bit in a little bit in the future. But as far as tornadoes go, think of it this way. If you have like warm air, let's say that it's very warm in your house, right? But it's very cold outside. What happens when you open up the door? You usually feel the wind hit your face, right? That's because any weather and any warmth, any pressure always tries to reach equilibrium. It always wants to be the same temperature. It always wants to be the same pressure. It always wants to have the same amount of moisture. It always wants the same everything. So the Earth is constantly trying to make sure that everything is always in equilibrium. So when you're looking at the United States like this, tornado alley is here. It's because there's cold, dry air coming in from Canada or from anywhere over the Rockies. You have warm, dry air coming in from northwestern Mexico, and you have moist air coming from the Gulf. When all those mix together, it creates tornadoes. It's basically the perfect storm of making sure that all the dry air, the cold, dry air, and the warm, moist air come together and start to rotate and really create a lot of tornadoes. That's why you always hear tornadoes forming in this one area. It's just unfortunate because it's perfectly made to create tornadoes. You guys have any other questions as far as tornadoes are concerned? I'll talk a little bit more, but do you guys have any questions about how tornadoes form? You could either shout it out or just raise your hand. Your teacher could call on you.
They seem to be fairly enthralled. They're good.
All right. Any questions about hurricanes at all? I'll be talking about that more as well. But do you guys have any questions about hurricanes and how they're formed or anything else? Why they hit you guys rather than they don't hit anywhere in Minnesota?
Is a hurricane exactly like a tornado, but it goes over the ocean? Yeah.
That's a good question. There are a lot of differences between hurricanes and tornadoes. Obviously, the big difference is size. Tornadoes, at most, they're maybe a mile or so. On average, they're around a mile or so. So let's say that you're looking at, let me load up the map again. Tornadoes, you will barely see them on the map, even if I zoom in. If I zoom in even more, like, let's say, you guys are right here, okay? Our tornado may be only from here to here as far as length goes. Very, very small. Meanwhile, a hurricane could be spanning from one side of Texas all the way through Texas to Louisiana to Alabama as well. So as far as size goes, tornadoes are very small versus hurricanes, which are very wide. So hundreds of miles across versus on average, usually a mile or less across. As far as how long they last, hurricanes could last days. They could last weeks, if so. The longest one lasted around a month, actually. It went through December all the way to January. So it's one of the only ones that went through the calendar year. So a hurricane, which could be over here, could last for days, then a week, then 2 weeks, go through, like hit Florida to Carolinas, to all the way to New York, and then go all the way over here a couple of weeks later, and then finally go away somewhere in the ocean. A tornado may only last for days at most. The longest one that lasted was 3.5 hours. It could go from, and it moves, while it moves very fast, it can maybe go from Fort Worth to, and then die out maybe over here. That's about it. So that's the second thing. Lasting at most, like maybe it could cross, you know how small Rhode Island is? It wouldn't be able to cross Rhode Island. Meanwhile, a hurricane could cross, like Patricia did, through Mexico, go through the Northeast, and go and hit Ireland. So that's another big difference. As far as how many of them, usually when you see hurricanes, let's look at a hurricane right now. I'm going to open up, where are you guys? Texas. I look up any hurricanes right now. There's nothing in the Atlantic and nothing in the Pacific. So great. I was going to give you an example. But usually with hurricanes, you only see one, at most maybe two, and very rare cases, three in a large area. That's about it. Because if you have two hurricanes, usually they merge together and they just create one big storm. So it's almost impossible for there to be more than one hurricane. Meanwhile, with tornadoes, you could see tens of them in a very small area. You could look down and you could see a storm, and with an eyesight, you could see a line of tornadoes forming. So you could see a lot of tornadoes instead of just one hurricane. And the last thing is how they move across. So you guys have seen weather maps. This is a surface map. So you can see here high pressure, low pressure. You can see fronts. When hurricanes come in, let's say a hurricane is coming in where my mouse is, over here on the very bottom right. If a hurricane moves in, it'll hit that front, and the front will usually move it across. So hurricanes are dealt with by large-scale winds. Tornadoes usually just stay within that storm system that are there. So if I load up the map of the systems again here, where all these are, I don't think there are any tornadoes here, but if I look here and look up any storm cells, you can see here just where storms are moving. So see that yellow? That means that there are damaging winds. So there may be a tornado in there if there's more energy. If I load up here, you can see how that tornado, the system is moving to the northeast. If there's any tornadoes, they usually move with the system. They don't deviate from there. They're not affected by large winds. They only go with the storm itself. So that's another big difference. Hurricanes moving in accordance to the jet stream outside, or if they hit any other systems. Tornadoes stay within the systems. The biggest thing, though, that brings them both together, they both are cyclones. So if you look at a picture of a hurricane, I think there's a hurricane, or there's a cyclone right here. Cyclones are hurricanes, by the way. So a hurricane just means that it's a cyclone in the northeast. It could be named an anticyclone over here, a cyclone over here, a typhoon if it's going towards Asia. But you can see here, there's actually a system right here. You can see how it's rotating around in a circle. Whenever, actually, I can show you a picture here. Where is... Let's try to show you guys tornado formation. Okay, tornado formation is here. So you can see here that tornadoes go around in a circle as it goes up. It always goes counterclockwise in a circle when it's in the north. And I'll mention that a little bit more as well a little bit later. But tornadoes you see go around in a circle as it goes upwards, right? Hurricanes do the exact same thing, except they're larger scale. So if I load up a hurricane here, hurricane formation, you can see here it does the same exact thing. Tornadoes are moving upwards around it, and then big downward winds in the center. Hurricanes are very similar, where there's circular rotation going up into the atmosphere, and then in the direct center, it goes down where the eye wall is. So there's a lot of, they look similar if you look at the rotation, but there are a lot of differences that you can look up as well, and how quickly they move or how slowly they move, and how they're created. And going back to your question of how they are created, as I said before with tornadoes, it's based on the convergence of cold air, dry air, warm air, and winds moving them into it. As far as a hurricane goes, the reason why they are always formed in the ocean rather than on land, it's almost impossible for regular tornadoes to form over the ocean, because all that air is going to be moist no matter what. Actually, funnels, when you see water spouts on the ground, I actually have a picture of one. There's fire tornadoes, there's a water spout. So when you see something like this with a water spout, that's a tornado that is over the water. One of the biggest reasons why you could see tornadoes, even though winds could be over 100 miles per hour, the reason why you see tornadoes is because they're picking up dust on the ground, or they're picking up debris on the ground, or there's clouds that are within them that are pulling up, or anything else that they're pulling up with it. The reason why you see tornadoes is because it's pulling up stuff on the ground, trees, grass, anything else, and you're seeing that debris going around the tornado. So with a water spout, it's pulling up just water. So this is a tornado, but it's over water. If there happens to be a fire like this, it could pick up fire as well to be a fire tornado. But the reason why they all form is because there's circulation in a very small area between different types of air, like warm, wet air or cold, dry air. For hurricanes, however, there's a big difference. There are, where are you? Hurricane paths. There it is. As far as hurricanes go, these are where they form. So if you look by the places that will hit you, Texas is right here. You guys are right here. Storms that form will always be in this very warm area. They pick up the warmth. They have winds that start to make it rotate. If there's enough energy because of the fact that the water is warm and there's enough rotation in the atmosphere, it starts to pick up more and more energy and becomes a hurricane. So it's only warm weather. There cannot be any higher winds that cut it off. Let's say that you are, what's a good analogy? Let's say that there's something moving across, like a plane, but then there's a wind that's blowing across it. What happens to the plane? It starts moving this way. If that happens in a hurricane, the winds can't form correctly. They break apart. There's no more hurricanes. So you can't do that. That's different from a tornado where you need that rotation to happen. But because it's larger scale, when this moves across, it needs to be over that warm water. If it's cold water, so let's say it's August through October. So we just exited the official hurricane season, but hurricanes could still form. So you can see over here, there's June to December. We're on the northern hemisphere. It's more summer. But if you go down to the southern hemisphere where Australia is, January through March is when it's usually cold up here, but it's summer for Australia since they're on the southern side. So they need the warm water to form here. If it's, let's say, you never hear about hurricanes in March, right? It's because it's too cold to create hurricanes. The water's too cold and you can't get any formation. Now, one thing that does create itself from hurricanes or tornadoes, another big thing that you guys mentioned was flooding. Flooding could happen if there's, in tornadoes or hurricanes. With hurricanes, it could be many, many hours of flash floods. And actually, if I go into my hurricane folder here, Hurricane Isaac and weather map, high, low pressure here. So with Hurricane Isaac, it was a weak storm, but it stayed in an area for multiple days. So you can see here, August 25th through September 3rd. That's 8 days. It hit where New Orleans is, right? And it caused some places 2 feet of rain. That causes a lot of flooding. So you can see over here as well. It's a lot of rain over a very long time. That caused a lot of flooding. So hurricanes, if you see that a hurricane is stalled out, so let's say that it runs into, this is a cold front, it runs into a cold front and stays where it is. It'll create a lot of rain in a very short time. And the hurricane that was just in, I believe, it wasn't Patricia, it was the one near it. I can't remember which one it is off the top of my head, but there was a hurricane in the Pacific that stayed over the Bahamas for 3 or 4 days and it caused massive flooding. Or it was, and then as soon as it passed through, it was fine. It just went fast. But because it stayed in a certain area, there's a lot of flooding that happened. Flash flooding is something that happens when there's a lot of rain in a very short amount of time. So if a tornado is by, you could see a couple of inches in an hour. And that's a lot to deal with, and especially if an area already is very wet from another storm. So you see flooding from that. If there's supercells like tornadoes, you could see hail, you could see heavy rain, you could see the tornado itself, you can see severe thunderstorms, and that creates a lot of flash flooding as well, which is also a big catastrophic event. On the flip side, though, if there's an area like, let me zoom out here, if there's an area like Nevada, that's a desert, right? Why is that a desert? Because over here with, you see this green area? That and anything over here, these are all mountains. When weather systems hit mountains, they go up, they drop all their rain, and past that, they have nothing. So instead of flooding, which is a lot of rain, these areas have very little to no rain, maybe a couple of inches every year at most. And because of that, you could have forest fires. You could have, which if there's droughts or if there's very hot weather, like heat conditions, which cause red flag warnings, that could cause catastrophic events like forest fires that are widespread. You hear that a lot in Washington because it could be hot weather and then there could be a lot of dry spots as well. So there's forests with a lot of forests that could deal with not having that much rain. But if somebody lights a cigarette, flicks it out into the water or into the forest, it creates a fire. Or if there's very hot weather, maybe a spark could form somewhere, and because it's so dry out, the forest is very susceptible to being on fire. We already talked about earthquakes and tectonic plates, tsunamis, which are by the earthquakes themselves. I want to show you guys something that I actually just found today when I was looking up stuff to talk to you guys about. This is the Earth, right? Here are global patterns in the Earth. So you guys are actually right there. So this is the Earth, and these are the winds that are moving around the Earth. So winds on the surface, you can see here, there's a high pressure system. You know it's a high pressure instead of low pressure because winds are going clockwise. It's going around in a circle clockwise. I could actually show you guys high versus low pressure here. So high pressure means it's moving outwards and it's moving clockwise in a circle. Low pressure means it's going towards itself and it's going counterclockwise. That's something big to keep in mind, because let's say that you look at a hurricane. This is Hurricane Floyd, right? The winds are going counterclockwise. And they'll always happen like that. If you look at tornado, it's always going counterclockwise.
Can you repeat what you said about high pressure, the rotation clockwise versus counterclockwise? They wanted to write that information down.
Oh yeah, sure. Let me open that up again. Sorry. So here we go. High pressure, and I could always send you all these files as well if you want to use this in lectures.
Perfect.
So high pressure, it moves outward, and it moves clockwise. So you can see. Can you guys see this picture clearly?
Yes.
All right. So you see here on the left, that's high pressure. It's moving outwards and counterclockwise. What that usually means, and again, high pressure means that there are very little clouds. Let's say that you have, actually you could do this experiment on yourself. If you have a glass of water and you take a straw and you swirl it around in a circle, what happens? It goes towards the center and in whatever direction you're spinning. The reason why it goes clockwise, though, clockwise when it's high pressure, but low pressure when you're going inside towards a circle, that's because of winds in the upper atmosphere. Do you guys know about the Coriolis effect?
Yes, they do.
So the Coriolis effect means that the Earth is rotating around, and it's a circle, and it's rotating around. But because of the fact that the equator has to move faster to rotate once in a 24-hour period, the winds are also moving faster. So towards the poles, and actually I could show you guys this here, right here. If I show you upper level winds, so 10 HPA. So this is showing you guys the upper level winds. You can see here that they are always moving faster here than they are towards that. And if you see on the equator itself, it has to compensate. So looking at the North Pole, right over here, the winds are very, very, very slow because they don't have to move. They really don't have to move at all. But as you go outwards, they get faster and faster. So the Coriolis effect, the reason why you see low pressure move like this is because of the fact that, let's say this is the equator right here, right? Winds have to move very fast here, but they move slower over here, which means that the wind will eventually curve around in a circle. That circle is this, the low pressure. It moves around in a circle exactly like that. That's why you see low pressure moving around in this way. And high pressure has to do the exact opposite because of the fact that winds are coming from the upwards, from upward to lower. So whenever you see high pressure, and you can actually see on a map here, where's my, let me start closing these out. So a weather map here, the high pressure is going to be going outwards, clockwise, and low pressure, you'll see here, the front is pointing which way? It's moving right, which means, and this front is moving up, which means that it's moving around in a circle counterclockwise. You'll always see that with weather maps. And if you look at today's weather map, you can see here, and I'll show you two things. One, the high pressure, again, is over you guys right now, so you'll see winds moving around this clockwise. With low pressure, if you ever look at it, over here, you can see here, low pressure is here. This wind, this cold front is moving from left to right. This warm front is moving from southeast to northwest. It's moving around this counterclockwise. You'll always see that. And if I load up that map that I showed you guys again of the lower winds, if I go right back to where you guys are, high pressure is right over you guys, right? So the winds are moving right here. There, you can see here it's moving clockwise. But where that system is, that low pressure is right over here, you could see it's moving in a circle counterclockwise. High pressure over here, very big. You could see it going counterclockwise and outwards. But go back to that hurricane that I was showing you back before, that leftover tropical storm, and it's moving inwards and counterclockwise. So you'll always see that. As far as large scale, if I zoom out here, you can see just how they interact with each other. So high pressure, can you see my mouse over here?
Mm-hmm.
So you can see high pressure goes out like thiswards, goes outwards, and then gets pulled into the low pressure, goes inwards, and starts going counterclockwise instead. So those two interact with each other. It goes outwards, so high pressure, and then low pressure inwards, and the opposite rotation. As far as the jet stream goes, I'll show you guys this. So you can see a picture. This is the Earth. Right here, this is U.S. Not much is happening. The winds are going fairly slowly. It's in dark blue, which means that it's not really moving too much. There's low pressure here. There's high pressure here. You have some winds going this way. You have a big high pressure over the northern Pacific. But if I load up the jet stream, which is, again, 5.5 miles up, if I load up the jet stream, all of a sudden it's moving in a completely different way. This is a low pressure right here in the jet stream. So it's moving which way? Counterclockwise. This way it's moving clockwise. This is high pressure right over here. Going low pressure, big high pressure over here. But right where that system was, over here, this is where the low pressure was, right? We can see exactly where it's moving because the jet stream is going to move this towards the northeast. It's going to move it northeast and then east. So the jet stream really moves systems in a very large way. Now, one thing that we learn, ridges and troughs. Troughs are like valleys. Ridges are like mountains. So you can see here, there's a big trough. This is low pressure. There's going to be very big wind gradients over here. This is a ridge of high pressure where the winds go back up again. Now, whenever you hear about the jet stream, let me go just show you again. These are the current winds. The jet stream looks like this. So those high winds are right here. The high winds are over here. The gap over here is high pressure, means that there's not much happening. Now, there are jet streams. There are a couple of jet streams on the Earth itself. I load up this right over here. The Earth has a couple of different jet streams. So the equator is right over here in the center. There's really nothing that goes on. It's an intertropical zone. There's not much that really happens. This jet is what you're seeing directly over you guys right now. Directly to the south of you guys right now. Anywhere that's south of it is very warm. Anything that's north of it is colder. You guys heard the term polar vortex?
Probably not.
Okay, so 2 years ago, you were using it in the media a lot, called the polar vortex. In the middle of a very warm month, all of a sudden you saw temperatures below the freezing mark. That's because this jet over here, the polar jet, dipped down so low that it actually went south of us. And because of that, we were seeing polar winds and polar temperatures. So this is a jet stream right over here, and that's exactly what... Let me load this up again.
So they've seen that image before, the one with the winds, when we talked about the easterlies and the trade winds.
Right.
That's the jets. Those are the names of the jet streams. Right?
Yeah. So those are trade winds. You have the subtropical jet, the polar jet. These are the westerlies. The northeast trade winds are here. So you could think of the Earth as split into 6 parts. On the northern hemisphere, the first third, there are 90 degrees in the Earth, right? The top to the bottom is 180 degrees. The center is 0. If you go up a third of the way to 30 degrees, those are northeast trade winds. So that little bit over here. From here to here, 30 to 60, that's where we are. That's where you see mid-latitude winds, the westerlies. And then when you go up to the very top of the Earth, those are polar winds. And they always go the opposite ways. It's just like how I showed you before, how you could go around here in a circle like this, and when you go this way, it goes the exact opposite way. So you see here, the jet stream is here with the opposite winds. If you go up a little bit higher as well, the winds get even bigger. So this, actually, let me go to 10 HPA. So this is 100,000 feet above Earth, which is 19 miles. And you can see here that they get stronger and stronger. The reason for that, as you go higher into the atmosphere, there's less and less pressure. There's less resistance. So if I load up this picture of this plastic bottle, the left side is on, this is on the surface. So this is near the water where you guys are, like on the surface of the ground. As you go higher up in the atmosphere, there's less pressure. So the bottle crushes itself a little bit more. And as you go up to the mountain, there's even less pressure. So the bottle is completely crushed. So think about if you go onto an airplane, right? Your ears pop when you go on the airplane. That's because you're going up into the atmosphere. There's less pressure, so your ears pop to deal with the pressure. That's important because, and that's the reason, another reason why planes go up into the atmosphere. There's less there's less resistance on them. They could go faster and not run into so many particles in the air. So that's why, like, for instance, when you go over here to this jet, this is the polar jet, winds are going very fast. Meanwhile, if I go back to the surface over here, I go back to the surface, there's nothing happening. It's maybe 5-10 miles per hour. But going back up to the higher latitudes, all of a sudden it's 100, 200, 300 mile per hour winds. That's a big difference there. And what's good about this map as well is, let me go back to the beginning here. You guys wanted to learn about long-term events. So there's winds here. I could also change this to be ocean. You guys have you guys learned about currents, ocean currents yet?
Yes.
Okay, so let me first show you guys a map of the currents. So these are the currents that are across the entire Earth. You guys probably have heard the Gulf Stream before. It goes right over here off the coast of Florida, goes up the Atlantic seaboard, and then all the way out. These are all different. Currents. When a rule of thumb is, if it's warm outside, like near the tropics, if it's going towards the polar, the polar North Pole, or going south towards the South Pole, it's going to be going from warm to cold as well. So that's a warm current. If that current is going from the poles back towards the equator, that's cold water going towards warm water. So it's going to be a cold water current instead. And you can see that here. Let's say that I go to the Gulf Stream. Gulf Stream is going to be warm, and it's going to be moving into colder water. So that warm water is going to be over here. This water inside of the Gulf Stream is going to be warmer than the water around it, because that stream is all warm. But if I'm going to this, and you can see here, this goes all the way up to close to the Arctic. Actually, the Arctic starts right over here, so it goes through the Arctic. But once that belt moves down again,
I think we're underneath your screen. We can't see all of that underneath your screen.
Oh, okay.
There it is. We can
right
see it now, up towards the north.
Oh, I see. The top's right over here. Okay. Yeah. So you can see right up here, this is the Arctic. When the water goes over to here, it's going north towards the pole, so it's all warm. But as soon as it comes back down again, it's cold water moving to warmer water. So you'll always see that. When it's going downwards, it'll be colder. This is an exception just because the warm water never stops. But you could always think of the fact that if it moves up, it gets warmer. It's warm water moving towards cold. And if it's moving towards the equator, it gets cold. And if I load up the currents right here, this is a map of warmth in the water, where the currents are. So you can see here exactly where the Gulf Stream is. It's snaking across the ocean floor. So it starts off in the Gulf over here, goes between Florida and Cuba, goes here, between the Bahamas and between Florida, up the coast, and then it goes all the way out into the ocean. That's the Gulf Stream. And it continues over to here, but it gets weaker because there's a lot less water. But you can still see here, as I zoom in, the currents continue to go all the way up to here before you can see here it goes right back down again. And this is a cold water stream that goes all the way back down and actually feeds right back into the Gulf Stream. These are like conveyor belts where they just go throughout the ocean, throughout the entire ocean from start to finish.
Someone might use the jet stream or the Gulf Stream if they were planning a sailing trip, or using that to help guide their trip decision. Exactly.
So if I load up like the stream here, if you're sailing and for some reason, if you want to sail across the Atlantic, which people have done before, it's very dangerous, but people have done it before, you might want to start over here and follow that stream because those currents will push you farther. You don't want to go against it because you're going to need a lot of winds to push you back. But the currents in the water will push you forward, and that jet stream, which is, once I load this up again, the jet stream will also push you from west to east very strong as well. So if you have sails, you might want to put them up because they'll push you forward. Because the jet stream starts pushing systems, but if you're sailing on the ocean, you might want to look at the surface as well. Most likely they'll follow the jet to a point, and you can see here the jet stream moves from this direction all the way over here. So it's coincide with it a little bit, but you also want to look at let's say a radar. We want to look at a radar and say, okay, if you're sailing as well, I want to load up a radar and see, okay, maybe I don't want to go today because there's a little bit of weather here. There's going to be stronger winds. There's going to be thunderstorms and showers, and I don't want to swim it. I don't want to sail into that. And you can see with any models exactly where they might be a couple of days out. So going back to that model before, we have today looks like this, exactly like this. Let me zoom in a little bit as well towards where we were trying to hypothetically sail. You're sailing over here, right? If you go a little bit farther in the future, now this is Monday night, now it's Tuesday. You don't want to end up right here where this showers and thunderstorms are, because you might, your boat might tip over and you could be in a lot of trouble. So forecasting and looking longer term will help you plan for your events that you really want to do.
When does the Gulf Stream go through the land instead of bouncing off of it? Or so why, Khalil, can you specify that a little bit more?
Sure.
Why doesn't the stream go to the land? Like it showed the red and blue arrows bouncing off the land on the other picture.
So the red and blue arrows, it showed them bouncing off the land, but not going onto the land. Are you talking about the wind or the ocean?
Oh, you're talking about the ocean currents, right?
Yeah.
Okay. So with ocean currents, you guys know, have you guys been to the beach, or what waves are, where they crash up against the beach and they form little waves on there? The water can only go so far. So when you see, let's say we go to, let's go to the Keys, the Florida Keys over here. The jet stream goes through this a little bit. So it goes right past it. If it hits the land at all, it'll just, let's say you have land over here, the water will go up to it and create some waves and splash over it, but it cannot go any farther. Only tsunamis could really go farther inland. That's because those waves are tens of feet high, or maybe even 50 feet high. That's the only way that they could go into the land, because of the fact that the water goes down below the ocean. The ocean can't rise up against it. You need a lot of energy. So you need like a earthquake to form and to push a tsunami to make it go inland, but you'll never see it go too far. And it can't cross through the water. So the ocean, let's say that you have the state of Florida here, right? You have this cup represents Florida. The ocean goes to here, or the ocean goes to here. It can maybe go up to where the land of Florida is, but it can't go through the land. You can't move through solid rock. So you'll never see like this part of the water on this side of Florida over here. You'll never see this water affecting this water directly. You'll only see it if, let's say, a hurricane forms or a storm system, and the moisture from that goes into the air and goes over the land before it drops down to the ocean again. But it can't go through solid land. So if you look at, let's say that I look at a picture of the Earth. Let's see. Actually, let me load up this up for you guys. Picture of the Earth without water. If you look at a picture of the Earth without water, it looks like this. Or let me find the United States. Right over here. So this is the United States without any water on it. Below the water is always land. The reason why we see a state like the outline of Florida is because that land, instead of it being so low in the ocean, now comes up all the way to the surface. So Florida would be here, and then it would be above ground, and then it would go down below again. So Florida, it's not just on the surface like this. It goes all the way down below the ocean. So eventually, at any part of the ocean, you'll see land. But the ocean is basically enough water that it fills up the gaps in the land until this looks like this instead, where you see states instead. But if I go through the ocean, you'll see land, but it's below the water instead. So the reason why the currents can't go through any land is because below what you see on the surface of the ocean, there's land below it, no matter what. Even if you go to somewhere like Hawaii over here, there's Midway Islands. Where's Hawaii? Right there. Even if you go to Hawaii, it's not just land that's floating on the ocean. There's not ocean going below it. If you go, there's volcanoes here because this land goes all the way down miles and miles and miles into the earth. So Below this, there's a lot in the ocean. Actually, I could show you a picture. Yeah, so you can see here, there's a volcano, but trying to find a good picture for you guys. Volcano into the water. Let me see if I could find this. I just want to show you a diagram of, okay, here we go. So you can see here, there's water here, but the land goes all the way down towards the center of the earth. So water can't go through it because there is land there. I hope that answered your question.
How do you know, or how did they discover the way the jet stream travels?
Have you guys heard of weather balloons?
Yeah.
Basically, those are big, let's see, weather balloons. So with weather balloons, they get filled up and they go into the sky. So they launch them here, and they're filled with helium. They go up into the air, and they actually expand so big because there's less pressure pushing them in. So when the weather balloons goes up in the atmosphere, it records the temperatures, it records the winds, the air pressure, and a whole variety of different measurements. So when they first launched these, they launched up into the air, and all of a sudden, when they got higher and higher, the winds got more and more and more until they reached that jet stream place. They saw it was 300 millibars. It was 5.5 miles up, or 30,000 feet up, and all of a sudden the winds went to 300 miles per hour. They eventually saw that and realized the anatomy of what it looks like. If I load up a sounding,
He had the same question, but with the Gulf Stream as well. So
okay, yeah.
both. Yeah.
So if I look up a weather sounding, you can see here when the balloon is launched, it starts off on the ground. It's fairly one. You guys have seen weather barbs before to know what it looks like when winds get faster. The more lines on a weather barb, the faster the wind. So you can see here, there's very little winds, but when it goes up over to here, all of a sudden you see these winds go up to over 100 miles per hour. These are the measurements that those balloons take. So as they get released into the atmosphere, they go up more, they record the pressure, the temperature, the winds, and a whole variety of other measurements. And they saw that the winds got very, very large up on the jet stream. And the way that they measure the jet stream now is by a couple of things. They have satellites that measure a very large amount of area. They have computers that project the models as well. And there's a lot of different instrumentation that records it nowadays. It makes it a lot easier for us to see where the jet stream is because of that. I had a picture here. I think I lost it actually. But I had a picture of where everything was in accordance with the jet stream. So what other questions did you have about the jet stream?
Those were the only other jet streams. And the last two went back to hurricanes and tornadoes.
Okay.
Why don't hurricanes ever hit Grapevine? So we're far enough inland. I think that question was about that.
Okay, I have a perfect answer to that. Hurricane Pass. I actually have an image of where all hurricanes ever were. So once I load this, it'll take just a second to load. Let's say that I load up the Dallas area where Grapevine is. I'll click right here. You guys are right over here. Set area map right over here. Okay, and I'll make this 100 miles long and search that. So the reason why these are all the hurricanes that have actually went towards you guys. There are 27 hurricanes in the past. It looks like 70, I think it's 70 years. It goes back to 1954. Actually, this goes over 100 years. So there's one that goes to 1971. These are all the hurricanes that have passed through you guys. The reason why not many do is because if you look at any hurricane tracks, notice how all of a sudden where it hits here, it goes from going northwest all the way to going northeast, jets the other way. Remember those trade winds we were talking about before with this? When it hits that area, 30 degrees, all of a sudden, hurricanes like to change direction and go the other way because of the fact that those winds are pushing them to the east. And if I load up the distribution of hurricanes, most of them form over the ocean. By the time that they get towards where Texas may be, they're already starting to move east instead. So in order for a hurricane to come towards Texas, they have to go through this exact path just to reach you guys. Because if they go towards, let's say, Louisiana, by the time that they come over here, they may not even touch Texas because they're already turning to the right. They have to come directly in this way. And most of the hurricanes, when they form, they start to turn away a lot farther east. So they start to turn away in the Gulf, or towards where the Gulf is. They start to turn away towards where the Bahamas are. They start to turn away closer to the Atlantic. And you notice it's very, very rare for a hurricane to come through Mexico and go all the way over here. Because if you look at where the hurricanes form, they usually go out into the ocean. They're always going east to west, right? And you can see here, this line, see this big blue line over here? That line is this. That's where the jet is. You see the northeasterly trade winds? They're moving that this way from west to east. But as soon as you go over that jet and you see those mid-latitude winds from the west to east instead, those now start to go west to east. And that happens everywhere in the world. You can see here, it starts to turn again. It starts to curve. This way, it starts to curve the opposite way because it's in the south side. But most of the time, those hurricanes will go away from Texas because they would have to form, right here. Or if we load up where all those hurricanes were, all those hurricanes formed in a very specific way. And they moved in a very specific way. That's why there's only 27 that formed in a very short amount of time. Even if I load up the area, let's say that I set an area on map of, let's say, 500 miles. Let's type that in and set the area on the map to be right here where you guys are. Once that loads up, there's only a certain amount of more hurricanes, but most of them are going to be west of you guys. So once that loads up, all right, this is having a problem loading up for now for whatever reason, but it must be equal or less than 200 miles. Okay, in that case, let me set this area on the map. I'll go to Louisiana, just, a couple of hundred miles, let's say 200 miles to the east of you guys. There's going to be a lot more. Look at that. There's 111 hurricanes now. It's because most of these start turning away. You can see here, once they hit here, they start moving northeast, right? So they move that way before they even have a chance of hitting you guys.
Glad we don't live there. That looks much scarier.
Oh, yeah. And if you go to, let's say, Florida is notorious for having hurricanes, right? Click that. All of a sudden, that number explodes. Yeah, there's so much information that it gives me a warning. 200 different hurricanes.
Goodness gracious.
But you can see here all those hurricane tracks. Yeah, you see all those hurricane tracks? They move from this way, then move east again. So there's a big difference in that. And actually, I had a very nice image of world weather hazards. There it is. You can see here, that's most of the hurricanes. Most of them form here. There's very dark green, and all of a sudden it gets very light green because they rarely form that way. So that's all the hurricanes. And there's a couple of maps that show every single hurricane track. I think I might have had it. Tides. I'm trying to find it here. Okay, yeah, I don't have it. But there's a big detail. So you can see here, tropical storms, wildfires, tornadoes happen mainly here. As you saw here, that's Tornado Valley. Where else are there? There's El Nino events that it shows. So those are very large weather patterns. One thing I really wanted to talk about, though, do you guys know the difference between weather and climate?
Answer his question. Difference between weather and climate.
Climate says temperature and weather's like the sun.
What? No. You learned this in 5th grade. What? Climate is over a duration of time. Yes.
Right. Okay, so the best way, and I actually had let me see if I can find this. I had a good write-up about this. Do you guys know about the show Cosmos with Neil deGrasse Tyson?
No.
All right. There's a very, where's my video? He describes the difference between weather and climate. So red is climate. There's no fluctuations in it, right? But his dog moving, that's the blue line. That's fluctuations in weather over the short term. So over time, you can see here, over time, the climate stays the same. But in blue here, the weather changes as you go along. So weather is short term. It's hard to predict because let's say that something happens in say something happens in California. It comes across the United States, hits you guys in Grapevine. It changes that weather completely. So let's say that you have a 3-day forecast, very reliable. But if you go to a 10-day forecast, it's not as reliable because there's so many different things that could change. Weather could change incredibly well. You could have a cold summer. You could have a warm winter. But somewhere else in the world, you could have a warm summer and a cold winter because it offsets that. The climate is long-term, but it's also a global average. So last year could have been a degree warmer than this year for you guys. But the Earth as a whole, you could see the entire Earth's average temperature go up by half a degree. The climate is long-term, large scale. The weather is short-term on a smaller scale. That's a very big difference between the two. And it's a lot harder to predict weather because it's always changing, ever changing. But just like the jet stream, if I load it up once more, just like the jet stream, that's longer term. So we're able to easily identify where it moves because it's more predictable. There's a lot more data. There's a lot more statistics that go into it. So it's a lot easier to predict that versus weather.
We are a STEM school, so they're really interested in the technology and also like college career preparation for what this job might be like or pay in their future.
Okay, so as far as technology, that's the next thing I was actually going to touch upon. You guys know the biggest technologies that have really helped in the past just 30 years alone, radar systems. So if I load this up, all this is because of radar. You're seeing this because you're seeing the clouds because of radar. You're seeing the rain because of radar, exactly where all the precipitation is. This has improved in the last just 30 years alone. Let's say that you were in the 1970s, just 40, 50 years ago. There may be like a couple of 100 feet between different points on the radar, which means that there are a lot of gaps. You may not know what's happening within a storm. Now that's down to tens of feet. So I could even zoom into, you might have only seen just this large, as soon as it loads again, this large area. Let's actually right over here. This is severe thunderstorms over here. Loading out here, you may see this just as a blob, not too much. But nowadays, you can just zoom in so much like this. And once it loads up, my connection's a little bit slow right now. But once it loads up, you can see all these little divots. You can see these little holes in here. If I zoom in a little bit more, you can see exactly where these formed. All these cells, this is only maybe tens of feet wide, couple hundred feet wide. The radar has improved so much that now I could say, oh, if this is echoing like this, there may be a possible tornado. Or this right here, there's a little bit more wind. There might be a tornado forming right here. Just 20 years ago, this would have been more of a blob. You wouldn't be able to see it. That helps a lot because, let's say in tornado formation, just in the 1980s, if there are any tornado warnings, there's one either in your path or one's maybe about to form. You had 3 to 4 minutes to prepare. Nowadays, they're 14 minutes. Those extra 10 minutes means that families could have more time to go into the shelter, prepare, bring more stuff down there, or if they're on the road, travel into a safer direction. So radar really helps with seeing stuff in the short or midterm. You also have satellites. There used to be maybe a couple satellites just orbiting the Earth. Now there's hundreds, thousands of satellites. There are geostationary satellites, which stay in one point and just create loops on a certain area. Every 15 minutes, which is 1 degree of the Earth, every 15 minutes, it creates another loop of that area, so you're able to see what happens. There's polar satellites as well, which go around the Earth every 12 hours, and that creates different layers. Those two mean that we can now look inside hurricanes as well. You have a snapshot of a hurricane, you can see how it's moving every 15 minutes. It's easier to see if it's forming or not. It's easier to see if it's strengthening or weakening, and that data goes into models, which are what I showed you before, the model analysis, which is this. I'm able to see with the models that, okay, now it's Wednesday night. Oh, here's weather because I'm seeing those models. There's better models because there's better resolution. They see more. We now have more planes flying, eyes in the sky that could look into hurricanes and record, like Hurricane Patricia. All of a sudden they say, oh, wow, this is 893 millibars. There's 201 mile per hour winds. We're able to see that because there's planes that go into the center of hurricanes and directly record the data. And there's supercomputers as well. There are computers that are hundreds of times more powerful than the computers that you have at home that predict where all these weather systems move, that go into these models that are improved over the years, that have more data, that are able to crunch more data, that have more memory to be able to hold more data, that are able to move faster to process that data, to create better models in the longer term. Just today, you have a better 7-day model than just 20 years ago having a 3-day model. So as far as any jobs concerned, you could go into to use your career in weather to look more as far as research goes, to go into these models, improve them, to say, okay, well, what if I really do want a 10-day model that's really well? What can I do to help tweak those models? What data can I put into the models to make it better? You could go into a profession like I do, where you present weather on the radio. I could go into, let's say that I go into the weather and I'm looking at, I don't know, let's say that I'm looking at today's weather in New York City. That training will let me do today's partly sunny with highs in the mid-60s. Tonight we'll have decreasing clouds, lows lowering into the mid-20s. You know, it lets you learn to that. There's journalism that you could do. When you go into college, you could learn more. You could go into the ocean aspect. You could be a marine biologist, learn more about ocean currents, learn about ocean climates. You can learn about the ecosystems that go into that as well. Bless you. You can go into the ecosystems to learn more about, let's say, if you want to study dolphins. There's a lot of weather that goes into that, learning about the temperature, the climate that's in there. You can know what type of gear that you have to bring with you. Let's say that it's a warmer gear. You don't have to wear as much. But if it's colder out, you might have to wear a wetsuit with thermal protection. There's more of, I talked about the on-screen one. There's another job that I do that's forensic meteorology. I deal with lawyers where they say, okay, my client slipped and fell in February of last year. Can you let me know what type of weather went into that? With my training that I know, I could just load up any data that I want and say, let's say I go to Texas for you guys. I did this with one of the other classes. I'll go to Texas, I'll load up Dallas, and I could say, okay, the rain, the snow happened on this day. Let's say, okay, let's go to Dallas Airport, Fort Worth. And you guys had a big snowstorm back in March, right? So I could load this up, load up the hourly data, and with my training, I could just look at this for just a split second and see, oh, okay, well, here's all the rain. That's not the storm. The big snowstorm that you had was right over, where are you guys? You're over here, where you see a lot of data. And you can see, oh, okay, temperatures are below freezing, and it rained X amount, it snowed X amount. I could see exactly where it is, and I could write up a report going day by day by day. This day was warm. This day was cold, which means that temperatures froze down. Water on the ground may freeze and form ice, which they fell on. So you could look into the future with weather, trying to predict what's going on. You could look at what's going on right now to say, okay, why is this weather severe thunderstorms? Why is there a squall line? Why is this nothing over here? Why are you guys in sunshine? And you could look at the past as well and see what formed, what went into certain storms. Like we could look at Hurricane Patricia and say, okay, these factors are what caused Hurricane Patricia to form. Why did it do that? How could that help us predict future storms? So there's a lot of technology that goes into it that you could work towards improving, that you can interact with, that you could learn to create better forecasts. And anything that you do in college, there's a lot of different aspects that you could do. Again, you could go into research. You could go into marine work. You could storm chase as well. You could go into more presentation and education as well, teaching other people about all different types. You could go into, if you like hunting at all, you could go into planes and hurricane hunt. You could to fly over other storms to see exactly how they're formed. It even helps if you want to go into space engineering as well. There's a lot of weather patterns that you need to study that you could study if you go, like NASA astronauts, they love taking pictures of weather systems because they're so intriguing. But knowing about that really helps with figuring that out and where the systems move and how to predict them. So there's a lot of different.
How many years of school or college and stuff like that did you have?
So I first learned about this in 8th grade, it was either 7th or 8th grade Earth Science. It was around the same time that you guys are doing this right now. And I had a teacher that really got me into it. So I started looking at it on my own for the 4 or 5 years through high school. But I had 4 years of education with college to help me prepare this. My degree is atmospheric and oceanic sciences, so it encompasses everything.
I want to know where you got your degree.
Oh, Stony Brook University in New York.
New York.
Yeah.
They want to know where you are right now.
So you can probably see.
Let me show you.
So Stony Brook is over here. So let me zoom out again. This is New York, right? Long Island is over here. Stony Brook is right over here. I used to live there. Now this is New York City. I live right over here. So actually you can see, you guys over here, see where all those stars are? I am right over here. If you want to measure it out, measure distance, go all the way to where you guys are, right over here.
Yet another example of technology allowing me to speak to someone
Exactly.
hundreds of miles away.
Yeah, this is 1,400 miles away. And you can see here it's curved. That's because of the curve of the Earth. But yeah, the technology lets me see you guys 1,400 miles away. It lets me see the weather in Europe thousands of miles away. It lets me see it 3,000 miles away from where I am in California. It lets me see literally around the Earth. This is the counterpoint to where I am is somewhere over here. You know, I can see around the Earth and see exactly where the weather is. In Australia, which takes 22 hours or 18 hours to get to. So the technology helps us see around the Earth and helps us better predict that, because now I can see going around the Earth where those systems are.
Excellent. Well, we really appreciate your time.
Yeah, no problem.
They are very appreciative. What do we say?
No problem. So if you have any other questions, just send them me in emails, and I'll send you a link of all the other things that you do, even weather experiments that you guys could try it on your own.
Oh, excellent. That would be super.